Greetings, calculus students. This lesson is on logarithmic derivatives. Our first slide includes here a review of the graphs of logarithmic functions, as well as some very important log properties that we will be using throughout this lecture. Recall the graphs of logarithmic functions and the properties of logarithms shown below. Now, before I look at the graph, let's just quickly remind ourselves what a logarithm is by analyzing this statement. Log base b of a is equal to c. This implies, and is implied by, this is a double implication arrow, the base of the logarithm raised to the c must be equal to this a. This first statement is known as the log form or logarithmic form, and the second statement is exponential form. Just as a quick example, let's think about what log base 2 of 8 is equal to. You can put a question mark here, and to resolve this, we want to ask ourselves 2 raised to what power would be 8? And we know that 2 times 2 times 2 makes 8, so we need 2 to be raised to the third power. So log base 2 of 8 is simply 3. Now, not every logarithm can we come up with an easy exponent. For example, log base 2 of 5 is not a simple number, but if you reach for a calculator, we can determine that this is an irrational number that is approximately 2.32. Okay, while we're at it, why don't we just continue with these log properties, and then we'll look at the graphs. When you have a logarithm of a product, a times c is the product, then you can rewrite this as log same base b of the first factor, and then plus log base b of the second factor. Now, you don't always need parentheses around your arguments. You could put some parentheses around the a and the c, but when your arguments are very simple like they are here, often we just leave the parentheses off. Okay, now, what if our argument of the logarithm is a quotient? Here, you can rewrite this logarithm as log base b of the numerator minus log base b of the denominator. What if our argument of the logarithm is an exponential situation, a base with an exponent, a raised to the c? Then this exponent c can actually be brought down and written as a coefficient of the logarithm instead. So we can write this as c times log base b of just a. And this last one, we're going to demonstrate what's known as the change of base property. If you have any logarithm, log base b of a, you can rewrite this as a fraction of 2 logs instead, where the argument of the numerator is the same argument, a, and the argument of the denominator is what used to be the base. And then these logarithms have any base that you want, as long as it's a legitimate base. And for logarithms, bases have to be positive, but not 1. And you can choose any number you want. So if you go with base 10, just leave the base off. Recall that if you have a logarithm of a and there's no base written, then the default base is a 10. Also, if you have an ln, which I usually write as cursive, then this is simply a logarithm whose base is Euler's constant e, and it's called a natural log. So using the change of base property, we can continue. What if I choose my bases c to both be e? Then I can write this as natural log of a over natural log of b. And the possibilities here are endless because you can choose any c you want. Okay, now let's focus on the graph. I've just typed in y equals log base b of x. Add a slider for b. Let's restrict this from 0 to 10, step size 0.1. Notice when the base is 1, there is no graph because the base is not allowed to be 1. But if the base is less than 1, we get graphs that are decreasing that go through the 0.10 and follow the y-axis as an asymptote, with slightly different curvatures depending on my choice of that base. Now, if the base is more than 1, we get increasing functions whose curvature changes depending on how large that base is. But notice that all these graphs go through 1, 0 and follow the y-axis as an asymptote. So in our notes, 1, 0 will be an important point. If the base is more than 1, we have a growing exponential that follows the y-axis as an asymptote. And if the base is between 0 and 1, we get a decreasing logarithmic graph also going through 1, 0, and the limit as x approaches 0 from the right will be positive infinity, meaning the graph goes up along the y-axis as an asymptote. Now, neither one of these graphs have a horizontal asymptote. This green arch does climb up to positive infinity eventually. There is no horizontal asymptote. And this red curve will drop to negative infinity eventually. There is no horizontal asymptote. Furthermore, recall that if you have a logarithm, its argument, which in this case is x, must also be positive. The domain of a logarithmic function is only positive inputs. This is why we only see graphs in the first and fourth quadrants. There are no points over here in the second and third quadrants. Okay, use the graph of the function shown below to predict the graph of its derivative. We're working now specifically with y equals the natural log of x. Well, the natural log has a base that's e. E is about 2.7. Now imagine a point on the curve, such as right here, the orange dot. The slope of the tangent line here would be very steep but positive. And as you imagine the tangent lines, the steepness of the curve is decreasing but still positive. And as we go along the curve, the slopes continue to stay positive but decrease. They become flatter, less steep. Here I've programmed technology to show us the tangent lines and reveal the slope. You can see when the point is on this portion of the curve, we have very steep slopes. As the orange point moves, we get slopes that are going down in value but staying positive. Right here at the x-intercept 1, 0, the slope is 1. And then the slopes just continue to decrease but stay positive as we move along the curve. And that pattern will continue forever. Now if I reveal the graph of the derivative, you can see that for any x value, the slope of the tangent line, when you plot it as a y-coordinate, produces points along this orange curve. Pausing here at x equals 4, the slope of this tangent line is 1/4, and so the graph of our derivative, when x is 4, should output that slope of 1/4, putting our point right here. So here in my notes, right here at the x-intercept, the slope of the tangent line is 1, so we expect the output of the derivative function to be 1. Between 0 and 1, the slopes are very positive, but decrease towards the slope of 1. And then after 1, the slopes stay positive, but continue to get closer and closer to 0. So we expect the graph of the derivative to be something like this orange curve. We're going to confirm this on the next page. Moving on. Use implicit differentiation to find the derivative of the log function. And here we're given just a general log statement, y equals log base b of x. Our goal here is to find y prime. I'm going to do first is rewrite this in exponential form. The base b raised to the y should produce this x. And here's our exponential form. Furthermore, recall that the derivative of a constant raised to a function is equal to that same exponential function times the natural log of the base times the derivative of the exponent. This was discussed in a previous lecture, and we're going to need it right now, because I'm going to differentiate both sides of this exponential form with respect to x and use implicit differentiation. So when I differentiate b to the y, keep in mind b is a constant, but y is a function. So we should get itself times the natural log of that base times the derivative of that exponent. And now I want to differentiate the other side of the equation. The derivative of x with respect to x is just 1. This puts me in a position now where I can solve for y prime. So I'm going to divide both sides by b to the y natural log b. So y prime is equal to 1 over b to the y natural log b. If I can convert any y's I see here to x's, this would be ideal because the original function was presented as a function of x, and I would like its derivative to be a function of x as well. This portion right here, b to the y, is the same thing as just x. So the simple fix here is just change what's highlighted in orange back to just x. Okay, summarizing what we just discovered, the derivative with respect to x of log base b of x is given by 1 over x times the natural log of that base b. Of course, remember that we do have restrictions on what the base can be. The base has to be positive, but not 1. Okay, find each derivative below. Compare the graph of your last derivative to your prediction on the previous page. First one, the independent variable is z, which matches our argument of the logarithm. Here we have a log whose base is 2. So using our formula above, we know that the derivative of log base 2 of z will be 1 over that independent variable, and then times the natural log of the base. Notice I cross my z's so that they don't look like 2's. Next one, independent variable y, which is also the argument of this logarithm, which has a base of 1/2. The derivative is 1 over the independent variable y times the natural log of that base. And I'll write 0.5 as 1/2. Next example, this is a logarithm that has no explicitly written base, which means the base is 10. The independent variable is v, which is the argument of my log. So the derivative of this logarithm will be 1 over that independent variable times the natural log of the base. And in this last case, the natural log of x, something interesting is going to happen because this logarithm has a base of e. The independent variable is x, which matches the argument. So the derivative of this logarithmic function will be 1 over x times the natural log of e. However, the natural log of e is 1 because 1 is the power you would put on e to produce e. So we simply get 1 over x as the derivative of natural log of x. Looking at our technology, I graphed the derivative by simply typing f prime of x, but now I can change that to 1 over x, and it makes this graph that matches what f prime was saying. Notice that we also get this portion of the graph of 1 over x over here in the third quadrant. The only portion of this orange graph that's relevant to the black graph is the portion of the orange graph here in the first quadrant. Because this x in our logarithm must be positive, this suggests that the x in our derivative should also be restricted to only positive. So in Desmos, I would say restrict it to x only being positive, and then we get the portion of the graph that's relevant. Okay, let's go to the next page. Use implicit differentiation to find the derivative below, then generalize your result. So we're complicating the situation by putting an argument here that's no longer just x. I'm going to express this in exponential form. So b raised to the y would be equal to this argument. Now I'm going to differentiate both sides with respect to x again. Use implicit differentiation. So on the left, we still get b to the y times the natural log of b times y prime. And on the right, we get the derivative of the argument, which, using the power rule, will just be 12x. The plus 1 goes to 0. And then solve this for y prime. So we have 12x divided by b to the y natural log b. But then remember that b to the y is this b to the y, which is just equal to 6x squared plus 1. And then times that natural log b. So this is the derivative of this function. We'll stand back and look where the pieces are. The argument we see right here in the denominator. We see that next to it we have a natural log of b. And in the numerator we have the derivative of the argument. So we can generalize this so that I don't need to repeat this process every time. So if y is equal to log base b of u, then I can go straight to this. Y prime will be 1 over that argument times the natural log of the base, but then multiply by the derivative of the argument, which I can just put in the numerator. So we get this general formula. Okay, recall the derivative below. Here we have a function that's the absolute value of x, makes this v. We have a sharp corner at the origin, so this function is not differentiable at the origin, but everywhere else it is. For any point on this portion of the line, the tangent line would be also that line and would have a slope of 1. So the derivative of this portion I expect to be 1. And for every point on this portion of the curve, the derivative would be -1 to match the slope of that line. More formally, I can say this, that we're going to differentiate a piecewise function. The absolute value of x can be thought of as the graph of y equals x if x is bigger or equal to 0, and the graph of negative x if x is negative. So we can now differentiate these separately. So we get a piecewise function that's 1 if x is positive and -1 if x is negative. Notice I no longer have a partial equal sign on either of these. That's because the derivative is not 1 or -1 at 0, because at 0 we have a sharp corner. Well, another way to write this piecewise function is to say absolute value of x over x. Let's confirm this with technology real fast. So I've graphed absolute value of x over x. You can see it produces a function that's horizontal constant +1 if x is positive, and a horizontal constant -1 if x is negative. Let me hide that and type in f of x equals absolute value of x. And then if I just type in f prime of x, we'll automatically graph its derivative, producing this purple graph which matches the red graph, confirming that the derivative of absolute value of x is absolute value of x over x. So now we're going to explore then what's the derivative of the natural log of absolute value of x. Remember, the argument of a logarithm must be positive. So if I have absolute values on the x prior to doing the natural log, it tells me that the only domain restriction is that x can't be 0. X can be negative now because the absolute value of a negative is a positive, and then you can do the natural log of that. So when you graph the natural log of absolute value of x, we get two graphs effectively. We get the graph of natural log of x over here, and then its mirror image over here. We've doubled our domain by putting an absolute value on this x. How does this affect the derivative? Well, I can lean on this general rule that we've just created up here, because my argument, which is u in this case, is just absolute value of x. And so the derivative of natural log of absolute value of x will be the derivative of the argument over the argument times the natural log of the base. And the base here is e. Again, that natural log of e is a 1. Furthermore, the derivative of absolute value of x is absolute value of x over x. And now we have to divide by absolute value of x. We're going to invert and multiply. Think of this absolute value of x in the denominator being over a 1. So we're going to multiply instead by 1 over absolute value of x. And then observe we get cancellation of these absolute values of x. And so in the end, the derivative is just 1 over x again. We'll compare that to the prior page. We said the derivative of natural log of x was also just 1 over x. And now we're making the claim that 1 over x is still the derivative, even if the function is natural log of absolute value of x instead. Both branches of the graph of the derivative are now relevant. The left orange branch gives us the slopes of the tangent line of this left red function, and the right branch of the orange function gives us the slopes of the tangent line of the right red branch of this function. Okay, we're going to summarize all this now on the next page. Moving on. Much of what we just finished discussing leads us to the following results, which is really what's important to remember for this class moving forward. A summary of the logarithmic rules. So on the left, we have more general log statements. Notice I have bases b, where the base must be positive, but not 1. And then more specifically, we have the rules for when we are differentiating natural log, where the base is actually e. Okay, independent variable x, it does not match this u. We're assuming u is a function of x, and this base b we're assuming is a positive constant, where that constant must satisfy these conditions. Notice there's absolute values on the u. Well, we just discovered that when I differentiate this function, the absolute value bars disappear, and the result is as if there are no absolute value bars. So we get the derivative of the inside of the absolute values over inside of the absolute values times the natural log of that base. The absolute value bars can effectively be ignored. So the next one is the same function, but the absolute value bars are removed, and the formula is the same. It doesn't matter if the absolute value bars are on the argument or not, the derivative formula is the same. Now specifically, notice I've now changed the arguments to x, which do match the independent variable. So we won't need the chain rule here. We're going to get 1 over x natural log b in both cases. I am technically using this rule even in this case. So it's appropriate to think chain rule and put an x prime up here. However, since the independent variable is x, we know that x prime is just 1. So we just need to have a 1 there. Now in these next 4 cases, when the base is e, all of these natural logs of the base will become natural logs of e, which are 1s, meaning that you don't need to write them. So when you're differentiating with respect to x, natural log of a u, the derivative of this will be the derivative of the argument, u prime, over the argument in both cases. And specifically, when the arguments are x, or absolute value of x, and x matches the independent variable, then the derivatives are simply 1 over x in each case. And of all 8 of these formulas, the one that's most general, if you're going to memorize only one of them, I would choose to memorize these ones. They are the mother formula, and if you have them memorized, then you can easily reproduce the other 6. But frankly, the derivatives we'll use the most are these 4. Let's see some examples of these formulas. Find each derivative below. Here z is the independent variable. I have a function of z inside some absolute values as the argument of my logarithm. So I'm going to use the first case of my mother formula. This 6 right here is just a constant times a function, so it'll stay. This sine z takes the role of my u, and the mother formula gives me that I expect to be 6 times u prime over u, natural log of the base, and the base is 2. This 6 can be put up in the numerator instead. So we have 6 times, and then we have to differentiate sine of z. Z is the independent variable, and the derivative of sine of z is cosine of z, over the argument, which is just sine z, right? We don't need the absolute values on it, and then times the natural log of the base. Now, if you want, you could rewrite the trig functions, because cosine of z divided by sine of z is the same thing as cotangent of z. So we could also say that we have 6 cotangent of z all over a natural log of 2. Okay, in the second example, y is the independent variable. Furthermore, I see a product of 2 functions. So I will need to employ the product rule, which is u prime v plus uv prime. Thinking of y as the independent variable, the derivative of y cubed would be just 3y squared. Right? I don't need a y prime here, because y is the independent variable, so y prime would just be 1, times my v, which is natural log of y, plus u, y cubed, times the derivative of natural log of y. So I get to use this formula here, where y is the independent variable. The derivative of natural log of y is just 1 over y. And we get 3y squared, natural log of y, and then I can simplify y cubed times 1 over y, and that becomes just y squared. Notice both terms have a y squared, so sometimes it's worth factoring. Factor it out, and we are left with 3 natural log of y, and then plus a 1. Okay, next page. Find each derivative in 2 ways. Notice we really just have 3 derivatives here, they're in pairs. One way using the chain rule, another way using log properties prior to differentiation. Derivative of natural log 5v. V is the independent variable. Our u in this case is this 5v. To keep u's and v's separate, make sure that you write your u's with a tail and your v's without a tail. Our formula for natural log of u is u prime over u. So we ought to get the derivative of 5v, which is just 5, with v as the independent variable, over the argument 5v. The 5's cancel, so we wind up getting just 1 over v. Well, that's interesting, because that's also the derivative of just natural log of v, as if the 5 wasn't there in the first place. Let's see why that is using a log property. Here we have natural log of a product. So using our log property, I can rewrite the function first as natural log of the first factor plus natural log of the second factor, and then differentiate this instead. Well, 5 is a constant, so natural log of 5 is a constant. So when I differentiate the first part, I ought to get 0, and then plus, and now we just have to differentiate natural log of v, where v is the independent variable, so we just get 1 over v. And you can see why that the derivative of natural log 5v is the same thing as the derivative of just natural log v. The chain rule approach and the log property approach confirm we get the same result. All right, this next example, t is the independent variable. We have a t cubed here. So the argument of this logarithm, we'll call that u, and it's t cubed. Notice there is no base written on this log, so we're assuming it's a base 10. And our mother formula tells me that I expect to get the derivative of the argument over the argument times the natural log of the base. So in this case, we differentiate t cubed, which is 3t squared, over the argument t cubed times natural log of the base. And notice that it simplifies. We have t squared over t cubed. So we'll get some cancellation of t's, leaving a single t in the denominator, so we get this result. Let's do this derivative next, using a property of logarithms first. We have log of a base to a power, so I can first bring that power down as a coefficient using a log property, and think of this function as 3 times the log of t. We're going to differentiate this instead. Well, the 3 will stay because it's constant times a function, and the derivative of log t is 1 over t times natural log of the base, 10. And so this is just the same thing as 3 over t natural log 10, confirming our result above using the chain rule instead. Now this third case, x is the independent variable. Notice there's absolute values. When we differentiate this, those absolute values will just go away as if they're not there. But this time my u is a fraction, and our mother formula for derivatives of logarithms would give me u prime over u times the natural log of the base, and the base is a 7. So let me get my setup going. We need to find the derivative of x over x plus 2, so I'll put a prime on that, over the argument times the natural log of 7. You can see why this is starting to look a little messy because we have complex fractions. Furthermore, in order to differentiate x over x plus 2, I would need to use the quotient rule. I have a v over a w situation. So just to differentiate that fraction, I would need to use v prime w minus vw prime all over w squared. So the derivative of v is 1 times w minus v times the derivative of w, which is also just 1, over w squared. Now instead of making a complex fraction, I'm going to take this natural log 7 and multiply it to the numerator of this fraction. Now instead of dividing by this fraction, I'm going to multiply by its reciprocal. So we're going to have times an x plus 2 over an x natural log 7. All right, let's continue to simplify. Multiplying by these 1s doesn't change the expressions, so we just have x plus 2 minus x. The x's will cancel, leaving a 2 there. Now we're going to multiply by x plus 2 over x natural log 7. This x plus 2 can cancel with one of the two x plus 2's I have down here, canceling that square and canceling this x plus 2. So I'm going to write my final answer here as 2 over x plus 2 times x natural log 7. Now this was a bit tedious because we had complex fractions, we had to invert multiply, we had quotient rule nested within chain rule. You're going to see how log properties can make this one a lot easier. So prior to differentiation, we have a logarithm of a quotient. So I can write this instead as log base 7 of the numerator, absolute value of x, minus log base 7 of the denominator, absolute value of x plus 2. Keep in mind that if you have the absolute value of a fraction, you can break this up into absolute value of the numerator divided by absolute value of the denominator. But this now is going to be the function I'm going to differentiate. And it's going to be a lot easier because I have subtraction, so I can differentiate function by function, term by term. So the derivative of log base 7 of the absolute value of x, the absolute value, as if it's not there, will be 1 over x natural log 7. And then the other derivative, I will need to use a chain rule because we have a u that's equal to x plus 2 here. So I will have a u prime, but the derivative of x plus 2 is just 1 still, over a u, which is x plus 2, times natural log 7. And technically I'm done. This is the derivative. It doesn't currently match the derivative I got up here. If I wanted to take the time to show that these two answers are the same, then I would need to get a common denominator so I can combine these two fractions together. So I'd multiply the first fraction by x over x, and the second fraction by x plus 2 over x plus 2. So I'd have a common denominator. So I have x plus 2 minus an x all over the common denominator. And then, of course, the x's cancel, giving us, as a final result, the same answer we got up here. Moving forward, I do recommend that when you're differentiating log of a function, that you consider using log properties prior to differentiation. In other words, I'm going to recommend that we do the methods you see down here. Okay, next page. Find the derivative of the function below in two ways. So both of these are the same. We have a rather complicated function that is a fraction with a numerator and a denominator. So I see the need for a quotient rule of this structure, and then we'll see where it goes from there. So y prime will be equal to, okay, so we're going to have to differentiate x cubed e to the x, which I'll do in a moment. So I'll just write it and then put a prime sign, times the denominator, minus the numerator, times the derivative of the denominator, and then all over the denominator squared. Now to do this derivative, this is the derivative of a product of a w times a z. I won't use u and v because they're already being used. So just to get that derivative, I would need to use the product rule, w prime z plus wz prime. The derivative of w is 3x squared times z, which is e to the x, plus w, which is x cubed, times the derivative of e to the x, which is just itself. So there's my derivative of the numerator times the denominator, and then minus the numerator. Now for this derivative, I'm going to lean on the square root of a function derivative rule, which will be 1 over 2 square roots of that function, and then chain rule times a u prime, which we'll just put in the numerator there. So the derivative of square root of x plus 5 will be the derivative of x plus 5, which is just 1, over 2 times the square root of x plus 5. And then this is all over just an x plus 5. All right, the very next thing I would do, because there is a fraction created right here, making this overall expression a complex fraction, is I would multiply top and bottom by 2 radical x plus 5. This term times this term gives me simply 2 times x plus 5. And we have minus this term times this fraction, just cancels. So we have minus x cubed e to the x only. And then all over. And then down below we have a 2, an x plus 5, and a radical x plus 5. Now there's more we could do to simplify this. I'll just do one extra step, but then stop. Notice every term has an e to the x. Furthermore, I can take an x squared out of these terms. So we could do some more factoring. Take an x squared and an e to the x out of the entire numerator. That would leave a 3 plus x in those parentheses times a 2x plus 5, and then minus an x. Furthermore, I can multiply these together because they're the similar base. One has a power of 1, the other has a power of 1/2. So I can add the powers and write this as x plus 5 to the 3/2 instead. And then you can multiply all this out to simplify what's inside the red brackets. We could keep going. But you can see that this has been a derivative rule nightmare and an algebraic simplification nightmare. But let me show you another way. So when you have a function that is a complicated mixture of products and quotients like you see here, that there's a method known as logarithmic differentiation that could make things a little bit easier for us. I'm going to take the natural log of both sides. So the natural log of y equals the natural log of this function. And I'm going to use log properties prior to differentiation. So we have natural log of y is equal to, and we have log of a fraction. So I can do natural log of the numerator minus natural log of the denominator. And now right here we have natural log of a product. So I can continue to use log properties. So you have natural log of the first factor plus natural log of the second factor, and then minus natural log of this radical. Furthermore, I'm going to view this radical as a power of 1/2. And now I can use a property where all 3 of these exponents can be brought down as coefficients. That gives me 3 natural log of x plus x natural log of e minus 1/2 natural log of x plus 5. And this is where I stop. Be mindful that there is no property for log of a sum, so I can't take this last logarithm any further. Also keep in mind that natural log of e is just 1, so I can just call this middle term just x. And now I'm going to differentiate both sides with respect to x and use implicit differentiation. So the derivative of natural log of y is a function of x, so we need to use the chain rule, and I'd get the derivative of the argument over the argument, y prime over y. The derivative of 3 natural log of x is just 3 over x. The derivative of x is just 1. And then we have minus 1/2 will stay, and the derivative of natural log of x plus 5 will be the derivative of the argument, which is just 1, over the argument, x plus 5. Keep in mind I'm solving for y prime, so as a final step, I'm going to multiply this y to the other side. And then replace that y with this function. So we have y prime is equal to the original function, and then times the rest of this. And this is a good place to stop this derivative. This process was a lot easier to do. It did not involve a mess of quotient rules nested within product rules, nested within chain rules, and then a lot of nasty algebraic manipulation. Now, of course, in order to show that these two answers are the same, I would need to continue to do some algebraic manipulation, which I'm not going to do in this lecture. Okay, one more page. This page is a summary of all possible cases of a base raised to an exponent. There's only 4 different possibilities. Case number 1. a constant raised to a constant. This is the easy case, because a constant raised to a constant is just a constant again, and the derivative of any constant is 0. So as an example, the derivative of 6 cubed is just going to be 0. Okay, the next case, right now let's do a non-constant function raised to a constant. So x is the independent variable. We're assuming u is a non-constant function, but b is a constant. This is the case where we use the generalized power rule. So that constant will drop down as a coefficient. The u base will repeat. The new power will be 1 less, so b minus 1, and then chain rule times u prime. This is called the generalized power rule. So as our example, we have the derivative with respect to x of a function raised to a constant. So the result will be the 3 drops down, the base repeats, the new power is 2, and then we multiply by the derivative of 6x plus 1, which in this case would just be 6. Now a constant raised to a non-constant function. So derivative with respect to x, a is a constant, v is a function. Furthermore, we do want that base a to be more than 0, so positive, but not 1. So this was the generalized exponential rule that we covered in a previous lesson. We get itself times the natural log of the base times the derivative of that exponent. We do not use the generalized power rule in this case. So as our example, we have a 6 raised to the 3x squared. The derivative of this function will be a repeat of the exponential function times, and we have the natural log of base, and then times, and we do the derivative of the exponent, which is 6x. And now we have a fourth case, which we've never seen up to this point. What happens when you have a non-constant function raised to another non-constant function? So neither the base nor the exponent is just a constant. Well, in order to do this, we're going to use this logarithmic differentiation we used on the last example on the last page. I'm going to begin by saying that y is equal to this u to the v, and then I'll do the natural log of each side, then use the property where this v can be brought down as a coefficient of the natural log, and now I'll differentiate both sides, in this case with respect to x. So the y, the u, and the v we assume are all functions of x. So the derivative of natural log of y will be y prime over y equals, now here I have to use the product rule, so we get the derivative of the first, v prime, times the second, plus the first v times the derivative of natural log of u, which is argument prime over argument, the argument being u. And I'm going to multiply both sides by this y. So we get y prime alone is equal to y times the rest of this. And then finally, I'm going to change this y back to u to the v. So here's my derivative. I'll just copy it up to this position. And we have a very general formula now for any situation where you have a u raised to a v, where u and v are functions. In fact, they could even be constants because this formula is general. This formula produces the other 3 if you replace u or v with a constant. For example, if u is a constant, then this u prime will be 0, hence this part of the formula will go away, and we wind up just reproducing this formula. However, if u is not constant, but v is constant, then this part would be 0, and this half of the formula would go away, and we'd wind up really just reproducing the generalized power rule. I'll leave it to you to show that that's the case. And if both u and v are constants, then this will be 0 and this will be 0, which means everything in the parentheses will be 0, and times this will be 0. And so we just get confirmation that the derivative of a constant is just 0 in the end. So this formula we just produced here is the mother formula for any situation where you have something raised to the something. The base and the exponent could be functions of x, or they could be constants. So our final example, we can just apply the formula, or you can go through the motions of doing logarithmic differentiation again, which is what I'll show here. Let's say y is this function. I'll natural log both sides, use the property of logarithms to bring that 3x squared to the front, and now do implicit differentiation with respect to x. So the derivative of natural log y will be y prime over y. Here I have to use a product rule. So the derivative of 3x squared is 6x times the second plus the first. And the derivative of natural log 6x plus 1 is the derivative of the argument, which is 6, over the argument. And then final step, multiply the y to this side. I'll get an 18x squared over a 6x plus 1 as that last term. And then finally, change this y back to this function. And I'll put my final result right up here. So the derivative of this function is equal to this function times, and then all of this, which I'll just copy and paste. Now, when you're working with this fourth case, if you want, you can commit this formula to memory and then just apply it and go straight to this answer. Or you can remember this process of logarithmic differentiation in order to reproduce this answer. Okay, this concludes our lesson on logarithmic derivatives.